I am Dr. D.K. Tripathi, Assistant Professor of Physics under the Department of Basic Science and Humanities.
In the last class, we have discussed the stimulated absorption as well as spontaneous emission quantitatively. That means in the last class we have started Einstein's theory of laser radiation and we have discussed the two types of transitions earlier. Today we will discuss the stimulated emission quantitatively. So for that, if we take tau st as the rate of stimulated emission per unit time per unit volume, okay, that means if tau st represents the time rate of transition probability from excited state to the ground state under the influence of external energy, then it will depend on the number of atoms present in the excited state. If large number of atoms are present in the excited state, then large number of atoms will interact with the incoming radiation and fall down to the ground state. If there will be less number of atoms present in the excited state, then less number of atoms will interact with the incoming radiation and will come down to the ground state with emission of energy. So it will be number of atoms present in the excited state, and it will also depend on the energy density of incoming radiation. If incoming radiation is highly intense, then stimulated emission will be high, and if it is less intense, then the rate of stimulated emission will be less. So from that we are getting two equations. Tau st is directly proportional to n2 and tau st is also directly proportional to u nu. Let us take them as equation number 4 and 5. Now combining equation 4 and 5, what we will get that tau st is directly proportional to n2 into u nu. Again the same procedure we will have to apply, because this will tell us that the tau st, that is rate of spontaneous emission per unit time, depend on the number of atoms present in the excited state and energy of incoming radiation. But to which extent they are depending, or the rate of stimulated emission will depend on number of atoms present in the excited state, and energy density will be given by bringing the equality sign. So here we will bring the equality sign, and for that what will be the constant, as this emission or this transition of atoms from excited state to the ground state is not natural one. Atoms have not completed their lifetime. They are compelled to leave the excited state because of interaction with the excited state atoms. So because of the interaction of the atoms as well as the energy which is coming from the outside, so that is what we can say that the constant of proportionality will be B. Why? Because this is induced emission, so B into M. Why? Because this transition started at the excited state and terminates to the ground state. So B into M into N2 into u nu. So we have got from equation number 1, then equation number 3 and equation number 6 is giving us the rate of absorption, rate of spontaneous emission and rate of stimulated emission. Now what will happen? Actually all these transitions of atoms are going on side by side. Okay, that means if we are taking the unit volume of some of the atoms which are in the ground state are absorbing the energy from the incoming radiation and are going to the excited state, that is absorption. Those atoms which have completed their lifetime, if they are coming down with the release of energy, that is spontaneous emission, and the atoms which have not completed the lifetime in the excited state, if they will interact with the incoming radiation, then they will fall down before completion of their lifetime under the influence of external energy, that is stimulated emission. So all these transition of atoms from ground state to the excited state, or from excited state to the ground state, are going on side by side. So we will have to know that what will happen at thermal equilibrium. So let us have the concept of thermal equilibrium. Thermal equilibrium means when the temperature of two parts of the same thermal system is same, or when the temperature of two systems are same. Now let us try to understand that if we take two thermal systems A and B, then if you allow the transfer of heat energy from system A to B, and if there is no flow of heat energy from A to B or B to A, that means the temperature of both of these thermal systems are same. What this means? That amount of heat energy in both of these systems are same. This is called as thermal equilibrium. This thermal equilibrium is also maintained in two parts of a system. So here what happens, that in this case of laser, as we have taken the collection of atoms, for simplicity we are taking the collection of atoms. This can be proved for the collection of molecules, or collection of ions, or collection of particles. So if we, in this collection of atoms, what will happen? That the temperature remains same at each and every place, because we have proved that very large number of atoms are gathered in the ground state and very less number of atoms are present in the excited state. So this does not mean that if rate of absorption will be high and rate of spontaneous emission and stimulated emission will be low, depending on the number of atoms present there, then temperature will be different at two different places of the collection of atoms. This will never be possible. If this is not possible, this means that rate of upward transition is equal to rate of downward transition at thermal equilibrium, because thermal equilibrium is maintained. If the temperature is same at every point of this collection of atoms, this means thermal equilibrium is maintained. So thermal equilibrium will be maintained only when rate of upward transition will be equal to the rate of downward transition. This means that what number of atoms are excited, the same number of atoms are de-excited by two processes, spontaneous emission and stimulated emission. So we can write tau AB is equal to tau SP plus tau ST. Now putting their values, we will get that if we write the value of tau AB from equation number 1 and the values of tau ST from equation number 3 and 6, then we can have B m2n n1 u nu is equal to A n2m n2 plus B n2m n2 u nu. Now let us try to find out. You see, B n2n is constant of proportionality, which will depend on the boundary condition. So we don't know its value. N1 is the number of atoms present in the ground state. This can be estimated, but we are not supplying, or we cannot alter them. U nu is the amount of energy which we are supplying, and this is in our hand. So that is why we will try to find out that what amount of energy can be given from the outside such that the stimulated emission can occur, because we have learned in the first and second lecture that stimulated emission is more beneficial than any other type of transition. So here our aim is to have the stimulated emission. So for that, what amount of energy should be given from the outside, that we will have to find out, and that can be found out just by finding out the value of u nu. So from here the value of u nu will be found out as A n to m n2 by b m to n n1 minus b n to m n2. If we look at equation number 7, which is energy density relation calculated by us, actually what is our aim? We want to know that what amount of energy should be given from the outside such that stimulated emission should supersede to the other two types of transitions. So what we are finding that energy density depends on the coefficients of spontaneous emission, stimulated absorption, as well as on stimulated emission. It will also depend on number of atoms in the ground state and excited state. But we want to know that what amount of energy should be given from the outside. All of them is not going to decided by us. So that is why we will have to we cannot say correctly that what amount of energy should be given. So equation 7 is an incomplete equation which cannot gives us the numerical value of the energy which should be given from the outside such that the stimulated emission should supersede the other two types of transition of atoms, either from the ground state to the excited state or from excited state to ground state. But this is energy density relation, so we will have to find out any resemblance of this equation which is derived as equation number 7 with any one of the established energy density relation. For that, if we consider the Planck's law. Why we will consider the Planck's law? Because Planck's law is given in the whole energy spectrum. You know that Wien's law of black body radiation or Wien's law of radiation as well as Lejean's law is not giving the explanation of the whole spectrum, whereas Planck's law explains the whole spectrum. So we will take the Planck's law. So from Planck's law, what we can write, u nu equal to 8 pi h nu cube by c cube into e to the power h nu by kt minus 1, where h is Planck's constant, nu is frequency of the radiation, k is Boltzmann constant, and T is the temperature, where also c is the speed of light. Now if we compare equation 7 and 8, what we are getting, that equation 8, which is a established energy density relation given by Planck's, is not having any number terms. That means it is not depending on the number of atoms present in the ground state as well as excited state, whereas our relation equation number 7 is full of number terms. So we will have to modify equation number 7. So for that, if we divide numerator and denominator of equation 7 right hand side by n2, then we will get u nu is equal to a n to m by b m to n n1 by n2 as well as b n to m and n2 by n2. So these two n2s, that means n2 in the numerator and also n2 which is multiplied by b n2m will be cancelled out, and we will remain with a n2m by, if we take b m2m m2n as common, then n1 by n2 minus, we have taken b m2n as common, which is not same as b n2m. So we will have to divide the term b n2m by b m2n. This is the law of mathematics, that if something is not present in other quantity, then if you are taking it common, then you will have to do the reverse process. If you are taking the common in the multiplication, then you will have to divide, and if you are taking it common in the division, then you will have to multiply. So we did the same thing. Now our task is to replace n1 by n2 in terms of some non-number terms. So from Maxwell-Boltzmann distribution law, n1 by n2 is equal to e to the power h nu by kt. we have proved it. When we are proving the number of atoms in the ground state is greater than the number of atoms in the excited state, at that time we have found the relation. So using this, equation number 9 will become u nu equal to A into m by, if we take b m2n as common, as I told you, then b m2n into e to the power h nu by kt minus b n2m by b m2n. Now you see, equation number 10 is the modified form of equation number 7. So we will have to compare equation number 8, that is Planck's law, with the equation number 10. Then we will get that b n2m by b m2n should be equated to 1. This will give us a very important relation, b n2m is equal to b m2n. What does this mean? This means that the rate of, actually what is this b n2m is what? It is the coefficient of stimulated emission is equal to coefficient of stimulated absorption. Will it be possible? Because b n2m depends on n2, which is very less. Number of atoms in the excited state is very less. We have proved it. And b m2n is dependent over n1. So this n1 is very high. In spite of that, if we are getting the equality relation between them, what does this mean? This means that the coefficient, if these coefficients are same, means that the two transitions are going on side by side, so they are numerically equal. The coefficient of stimulated absorption is numerically equal to the coefficient of stimulated emission. So this is called as Einstein's first equation. Now by comparing, again we will get a n2m by b m2n is equal to 8 pi h nu cube by c cube. So this is called as Einstein's second relation, and third relation will be got as a n2m by b n2m is equal to 8 pi h nu cube by c cube. If we replace b m2n from equation number 11b, then we will get this relation. So this is the third Einstein's equation. From that, what is clear, that the three equations, Einstein's equations, are very important for us. How? For that, if we go to the physical significance of them, then we will be able to know that. So physical significance of Einstein's A and B coefficients. For that, we will have to go the three equations which is established by Einstein. Now from equation number 11a, it is evident that the b n2m is numerically equal to the b m2n. What is b n2m? This is coefficient of stimulated emission is numerically equal to the coefficient of stimulated absorption. Is it possible? Just I told you. It is impossible. That means these two are numerically equal. And if these two are numerically equal, this means that the stimulated emission and the stimulated absorption are just the reverse process. What does this mean? This means that if in a system of particles or if in a thermal system, stimulated absorption is possible, means that if the atoms are taking the energy from incoming radiation to be excited, then stimulated absorption must be possible. Means that the atom will interact with the incoming radiation, those atoms which are in the excited state, and fall down with release of energy. So stimulated emission is just the reverse process of stimulated absorption. Stimulated emission is just the reverse process of stimulated absorption. This was the fundamental discovery of Einstein. Einstein told that this is not any unusual process. This is a usual process, that if the system of particles are taking, or thermal system are taking the energy to be excited, the particles if they are taking the energy to be excited, then they must take the energy to be de-excited before completion of their lifetime. From Einstein's equation number 11b, it is evident that the coefficient of spontaneous emission is directly proportional to the third power of the frequency. What does this mean? This means that in high frequency range or in highly energetic light, the spontaneous emission is highly probable. So, have you got the answer that why laser took so much time in its realization from the theory given by Einstein? It took nearly 40 years for realization. The cause is that in the visible radiation, which is very high, which is having very high frequency, you know that the frequency of visible radiation is 10 to the power 14 hertz to 10 to the power 16 hertz, which is very high. In that frequency range, the spontaneous emission is highly probable. So right from the beginning of our life, or right from our birth, we have seen very high frequency light, that is highly energetic light, in which the spontaneous emission is highly probable. So we were not having any concept of stimulated emission. It was Einstein who was a pioneer scientist in this and told about that. Also, from equation number 11c, it is suggested that stimulated emission is less probable in high frequency range. Why? In high frequency range, you have seen just that stimulated absorption is less probable, because if the light is highly energetic, why it will absorb from the incoming radiation? So we have seen from equation number 11b that stimulated absorption is rarely probable. We cannot say impossible. So what we are saying, that it is rarely probable in high frequency range. Like that, stimulated emission is also from 11c is also less probable in high frequency range. That means in highly energetic light, it was tedious to have the stimulated emission. So that is why the measure was invented at first. Microwave amplification by stimulated emission of radiation is a device which works in microwave range. Microwave range means power minus 6 meter is its wavelength. So frequency will be 10 power 14 hertz. So from that, because C equal to nu lambda, C is 3 into 10 power 8 meter per second, and if C is this, then from the relation C equal to nu lambda, what we conclude that the frequency of radiation will be 10 to the power 14 hertz. So this has just after realization of this microwave device, this has given us a way that how stimulated emission can be achieved in the case of the spontaneous emission. You probably know that maser was invented by Towns in England, and at the same time similar device was invented by Prokhov and Basov in Russia. So these three have combinedly got the Nobel Prize for the invention of this device maser. So we can say that in high frequency range, stimulated absorption was rarely probable. That is why maser was invented first, and this has given a way for the realization of.
In the last class, we have discussed the theory of stimulated emission given by Einstein, and we also discussed the physical significance of Einstein's A and B coefficient. So when this theory was given, then the scientists at that time thought that we will be able to devise a device which will have the monochromatic light. But there were several problems in the realization of that device. The cause was that Einstein has predicted about the stimulated emission. You just recall what is stimulated emission. Stimulated emission is that when the atoms or molecules or ions or particles in the excited state interact with the incoming energy and they fall down to the ground state. That means they will de-excite from excited state to the ground state with release of energy before completion of their lifetime. Then this is called as induced emission or stimulated emission. So for that, what we will have to do, if we want to realize this stimulated emission, then we will have to stimulate the atoms before the lifetime, and the lifetime of the atom in the excited state is 10 nanoseconds, that is 10 power minus 8 seconds. This time is so smaller that we were not having any device which can stimulate the atom before this lifetime. So at first the scientists have started the research, later on they were unable to devise the device. In 1940, Theodore Mammon, many scientists have done this, but the most important contribution is Mammon when he started to research over Einstein's theory. The stability of the atom in different energy levels was judged, and it is found that the stability of the atom or the lifetime of the atom in different energy state is same. While going through the atoms of different elements, when we have arrived to the chromium, it is found that near to the excited state there was another level where the atom can reside for 3 milliseconds. 3 milliseconds can be written as 3 into 10 power minus 3 seconds. 10 to the minus 3 second is 10 to the power 5 times greater than the time of 10 to the power minus 8 second, which is the lifetime of state. So atom can reside in this level to a greater time than the time in the excited state. So this level is having the stability of the atom or molecules or ion or particles for a longer time excited state, but less time than the ground state. But because the atom can reside in the ground state for a longer time or for infinite time theoretically. So because of that, what we can say that this state is a state in which the stability of the atom is greater than the excited state but less than the ground state. This means that the stability of the atom in this level is intermediate of the two levels, that is excited state and ground state. So that is why this level is metastable state or metastable state. Now meta, the prefix meta means medium. So medium stable state. Why it is called as medium stable state? Because atoms or molecules or ions can reside there for a longer time than the excited state and less time than the ground state. That is why this state is called as metastable state. So if atoms absorb the energy from the incoming radiation in the ground state, goes to the excited state, after completion of their lifetime in the excited state, some of the atom will fall down to the ground state directly, but most of them will be trapped in the metastable state. They will enjoy for a longer time. In the meantime, new set of atoms from the ground state will be excited to the excited state. After completion of their lifetime, they will fall down to the metastable state and some of them will fall down directly to the ground state. Now when they will fall down to the metastable state, at the same time earlier atoms are enjoying their time. So this will build up the population at the metastable state. So what we conclude that after some time we will be able to see that a very large number of atoms are gathered at the metastable state. The second problem in the realization of laser was that we have seen from the Einstein's theory that the rate of stimulated emission is directly proportional to the number of atoms present in the excited state. Now what we have seen, that the number of atoms in the excited state is always very less than the number of atoms present in the ground state. So if number of atoms in the excited state is less, then the rate of stimulated emission will be less, and if rate of stimulated emission will be less, then the strength, or we can say that intensity of the stimulatedly emitted light, that is laser light, will be very low. Then the properties of the laser light, what we have understood, that will not be found. So this was another problem in the realization of laser. That means if we want to realize the laser, then there must be very large number of atoms in the excited state. Whereas natural situation is what? Natural situation is that very large number of atoms are gathered in the ground state and very less number of atoms are present in the excited state. As per Maxwell-Boltzmann distribution law, we have proved it. For the realization, what we want? For the realization of laser, we want that very large number of atoms should be gathered in the excited state and very less number of atoms should be in the ground state, because total number of atoms are fixed. So we want just the reverse population of the atoms than the natural one, and that is why this situation is called as population inversion. So what is called as population inversion? Population inversion is the situation in which this situation is not the natural one. For the realization of laser, we will try to find it. So that is why this is called artificial situation. How to get it? For that, if you just recall the last slide, what I told you, that if energy is given from the outside, then the atoms in the ground state will absorb the energy and will go to the excited state. After completion of their lifetime in the excited state, some of the atoms will fall down directly to the ground state, but most of them will be trapped in the metastable state. As energy is continuously given, so continuously the atoms are going to the excited state. Continuously, after completion of their lifetime, some of them will fall down to the ground state, but most of them will fall down to the metastable state, where other atoms are enjoying their time. So if this is going on, after some time we will find that very large number of atoms are gathered in the metastable state and very less number of atoms are present in the ground state, and thus we have achieved the population inversion. That means very large number of atoms are in the metastable state, which is an excited state, and very less number of atoms are in the ground state. So the situation for the realization of laser is found out, or stimulated emission is found out. So how we can define this population inversion? We can define that population inversion is the artificial situation in which very large number of atoms are gathered in the excited state and very less number of, or better to say, metastable state. So how we can define? Population inversion is the artificial situation, or is an artificial situation in which very large number of atoms are gathered in the metastable state and very less number of atoms are present in the ground state, with the help of supply of external energy. How it is achieved? It is achieved by pumping. What is pumping? You just recall, have you pumped your cycle? In the cycle, when you are pumping, what you are doing? You are increasing the energy of your tubes. How? Because what happens that due to the continuous friction, the road and other environmental factors, the atoms which are in the excited state in the tires or tubes, they fall down to the ground state, and because of that the tires becomes, or tube becomes, fluffy. what you are doing? When you are increasing the pressure, because you know that P is equal to 2 by 3 E naught by V, where E naught is what? E naught is ground state energy and V is the volume. So when you will give the pressure, then energy will be itself increased. So that is why here the word pumping. Actually, pumping is what? Pumping is the process of achieving population inversion with the supply of energy. When we are supplying the energy to a group of atoms, then the atoms in the ground state will absorb this energy and will go to the excited state after completion of their lifetime. Some of them will fall down directly to the ground state, but most of them will fall down to the metastable state. So pumping is the process of achieving the different types of pumping. Just we have discussed that pumping is the process of achieving population inversion with the supply of energy. So in how many ways we can achieve the population inversion just by supplying the energy? That will be the different types of pumping. When we are supplying the light energy to have the population inversion, this is called as optical pumping. If we supply the electrical energy to get the population inversion, that is called as electrical pumping. If we supply the chemical energy to have the population inversion, that is called as chemical pumping. And if we supply the heat energy to get the population inversion, that is called as thermal pumping. Now these pumping types are not to be learned in detail. That is why I am not going to give you the example. Just in the last slide you have seen about the optical pumping. Optical pumping is what? When you are supplying the light, a beam of light, to energize the collection of atoms, molecules or ions or particles, that will be called as optical pumping. So we are not going in detail and just close these types of pumping or pumping here. The other problem in the realization of the laser was to give the directionality property or orientation of all the photons released either due to the stimulated emission or spontaneous emission in the same direction. How to achieve that? You must not confuse that the photons which are liberated due to the spontaneous emission will not contribute to the laser light. Certainly they will contribute to the laser light, but we will have to orient all of them in the same direction. How to achieve that? Actually what happens that if all of these photons will not be oriented in the same direction, then the intensity of the laser light will be very less, or stimulated emitted light will be very less, and that will not be the property of the laser light, because laser light is highly energetic, we have learned. So suppose at an instant of time, if 10,000 atoms from the excited state got de-excited with the release of 20,000 photons, now these 20,000 photons will define a wave. After 5 or 6 seconds, if again 10,000 atoms got de-excited from the excited state and liberate another 20,000 photons, so these 20,000 photons will again define a wave. So like that, there will be large number of waves due to the liberation of photons at different instant of time. Now if there will be very large number of waves, then there will be interference. If there will be constructive interference, then intensity of the resultant wave will be very high because of high energy. But if there will be destructive interference, then energy of the resultant wave will got decreased, which we do not want. So our aim is to have the constructive interference in this. For that, what we will have to do, for that we will, as shown in the figure, that we will have to take a device which is called as optical resonator. Now you see, in this optical resonator, what happens that we have taken two plane mirrors, M1 and M2. M1 is totally reflecting, whereas M2 is partially reflecting. Partially reflecting, that means up to 95% or 90% waves will go out and 1 to 10% will be feedback. Okay, so this wave which will come out, or the energy which will come out, that will be laser light. So that is why M2 is made partially reflecting, whereas M1 is totally reflecting, 100% reflecting. If the reflectivity of these mirrors are considered as gamma, then these walls, you are viewing the two horizontal walls, these two walls are made of absorbent materials. Absorbent materials are the materials which can absorb the photons. So those photons which will not contribute to the laser light, which cannot be given the directional property, they will be absorbed by these absorbent walls. Now what will happen? Then the waves which will interfere, they will have to you see, there are two benefits. One is that always 1 to 10% of the laser light will be feedback. So this will work as the oscillator. Not only that, we have allowed a condition to have the constructive interference. If L is the total length of this optical resonator, then we will discuss the working just in the next slide. Working of optical resonator. Now you see what we want. We want the constructive interference of the waves produced at different interval of time. So for that, what we know that for constructive interference, the phase difference should be equal to 2n pi, where phase difference will be equal to what? 2 pi by lambda into path difference. So in place of phase difference, we will write 2 pi by lambda into path difference. Path difference will be what here? If a wave starts, referring to the earlier figure in the last slide, if a wave starts from one of the position of the optical resonator, then in a complete round trip it will have to cover up 2L distance. So if you take the initial position as 0 and the total distance covered by 2L, then 2L minus 0 will be the path difference, that is 2L. So that is why we are writing 2 pi by lambda into 2L plus the reflectivity. What will be the reflectivity? Every body, any object in this world is having a reflectivity power, or what we call as reflectance. Reflectance is the property of the body by virtue of which it reflects the amount of light falling on it. So if the light is falling on a mirror, at the same time the same amount of light, some amount of the light will be naturally absorbed by it. That may be very less. As you see, that light falling on the mirror is reflected in more amount. At the same time, if the light is allowed to fall on the mica, that will be reflected in the less amount. So what we know that this is because of the reflectivity property, or due to the reflectance property. That means the reflectivity property will increase the phase. What is phase? Just recall. Phase is what? Phase is the time before which the particle was at its mean position. So phase is the time, it's not an angle. So here what will happen, if light will fall over the mirror M1 or M2, there will be some amount of delay in reflecting of that light. So 2 times in a complete trip, the delay will be seen in the phase. That is why we have used 2 gamma. If gamma is the reflectivity of one mirror, then 2 gamma will this phase difference will be increased by 2 gamma. So that is why we have written 2 pi y lambda into 2l plus 2 gamma will be equal to 2n pi. Now 2 will be taken common and that will be cancelled, so because of that we will get 2 pi l by lambda plus gamma is equal to n pi. Now anything which can decide property of the light is either frequency or wavelength. So that is why we will have to bring this relation in terms of either frequency or wavelength. So for simplicity, if we multiply the numerator of this equation by c, then we will get 2 pi lc by lambda is equal to n pi c minus gamma c. Now c by lambda will be frequency f. So this will give you the value of the frequency. F is equal to n pi c minus gamma c by 2 pi l, or if you segregate them, then you will get n pi c by 2 pi l minus gamma c by. Now let us try to find out that what are these factors. Frequency, actually what is this? This frequency is the frequency of the light wave which will contribute to the laser light, and other waves which will not have this frequency, they will not contribute to the laser light. So only those waves which will have this frequency, they will contribute to the laser light. Now let us try to find out let us try to recognize that what are these factors. N is order number, which is fixed quantity. Pi is fixed quantity. C is also fixed quantity. Gamma, reflectivity of a material, is also fixed. C is also fixed. 2 pi is fixed. L, length of the optical resonator, this is in your hand. So what we conclude, that we will have to take the length of the optical resonator such that most of the light or most of the light wave will interfere constructively. Now L for optical resonator can be made constant. So because of that, all of these factor will be constant. So what we conclude, that all will interfere there that will have the same frequency, and if they will have the same frequency, then resonance will occur, resonance of light wave. So that is why this device is called as resonator, and resonance of light wave occurs. For light the word optic is used, so that is why it is called as optical resonator. So a resonator, a device in which the light waves got resonated, is called as optical resonator. This is also called as resonant cavity. Why? Because most of the part of the optical resonator is hollow, so that is why it is called as a cavity in which the light waves are got resonated, or resonant cavity. Why it is called as resonant cavity? The same thing. This device was devised by Parrot for measuring the strength of. So a device which measures the strength of interference is called as interferometer. As it was devised by Fabry and Parrot, that is why it is called as Fabry-Parrot interferometer. So this device has got 4 names: optical resonator, or resonant cavity, or cavity resonator, or Fabry-Parrot. These are some of the references which you must pursue to know more about the topics. Thank you.